We've been talking about Newton's laws, net forces, and how a net force causes an acceleration. And today we want to talk about a special case of acceleration. And that brings us to a study of circular motion. So we want to talk about uniform circular motion, which means an object traveling at constant speed in a circle that has a fixed radius. This allows us to describe an object's position as it goes around a circle as it relates to the radius of the circle. So we're going to give it a position vector r. So when an object goes around a circle, that length of that vector stays the same because it's at the same radius, but its direction changes. Well, remember that velocity is displacement divided by time. So for our special case of circular motion, the displacement would be a change in r. And so instead of calculating velocity as delta x over delta t, we would say it's changing r over t. This velocity, if this was horizontal velocity, we would say this is velocity that has a constant speed, but this velocity is always tangent to the circle. And so we call it a tangential velocity. So what makes it tangent to the circle? Well, this is the velocity that's only going to touch the circle at one point, and it's going to be perpendicular to the radius. If something changed, if something happened, like if this was an object on a string going around in a circle and the string broke, or say for example you had an object that was tied to a string, like this blob, and you were twirling it around in a circle, and we would talk about which direction is it going at any point in time. Well, if we said when it gets over here to the side, which direction is it going? It's going straight up, perpendicular to the radius. But a short while later, when it gets to the top of the circle, you can see that it's moving to your left, still perpendicular to the radius. And as it continues on around its circle, the direction is always changing. Because the direction of a vector is always changing, and in this case it's a velocity, remember that we have a definition of acceleration as rate of change in velocity. And velocity is change in speed or direction. So if this was being twirled at a constant speed in a horizontal circle, but its direction was always changing, well then, by definition, since the direction is changing, the velocity is therefore changing, and therefore we are accelerating. And this is a special kind of acceleration. This acceleration has to be in the same direction as the change in velocity. Well, if we said that this object is moving up, and we want it to change its direction, to do that we have to pull in. And so as it wants to go straight, object in motion stays in motion, and we pull inward and that changes the direction, and we pull inward and that changes the direction, and we pull inward and that changes the direction. And so the direction of the acceleration is always inward toward the center. That's a special kind of acceleration. That special acceleration is called center-seeking acceleration or centripetal acceleration. Acceleration that's directed toward the center of a path. We call it A with a little subscript c. AC then is calculated as velocity squared divided by radius. So how do you get the velocity for something that's going in a circle? Well, remember the speed of something that's going in a circle is just distance divided by time. But what is that distance? Well, it's the distance that you travel around the circle. Remember, that's called your circumference. We calculate that circumference as 2 pi times the radius. So if we're looking at how fast something is covering this distance, we would do 2 pi times the radius divided by the time that it takes to go around the circle. That time is called the period of rotation or period of revolution. And so we use a capital T for that. So this velocity is 2 pi r divided by t. Well, if something is accelerating, Newton's second law says there must be a force that's causing it. There must be a net force that's causing it. So if this is a centripetal acceleration, then the net force that causes it is going to be the force that makes anything go in a circle. we can rewrite Newton's second law, F net equals m times a, for circular motion to be F net equals m times ac. But remember now, ac is velocity squared divided by radius. So F net would be mv squared over r. Well, what about that velocity again? If I get velocity as 2 pi r divided by t, then if acceleration is velocity squared divided by radius, and v is 2 pi r over t, I can plug in 2 pi r over t for v and square that, and we end up with, well, let's see, 2 pi r over t squared divided by radius. If we factor that out, 2 squared is 4, and pi squared is pi squared, times r squared divided by t squared, and then we divide that by r, we end up with 4 pi squared r over t squared. So this gives us 3 different ways to express the net force. M times AC, M times AC, which is still now V squared over R, or M times AC, which is 4 pi squared R over T squared. Well, why would I want to use different equations to give me the same stuff? Well, you've already learned that in physics, you don't always have everything that you need. Maybe they give you the acceleration and they want the force, but maybe instead of giving you acceleration, you're given the velocity and the radius of a circle, or part of a circle. And then maybe if instead of giving you velocity, they just give you the radius and how much time it takes you to go around. All of these will allow you to still solve for the net force. So let's talk about what that force is. If this is a centripetal acceleration, then this has to be a centripetal force that causes that. The net force, the force that makes something go in a circle, turns out for us could be one of maybe 3 things. So here, well, let's break it down. Here I have a car that might want to turn a curve on a road. So if you were leaving school and pulling out of a parking lot, you would make part of a turn on a road, and you would need to be able to have that force to allow you to make that turn. Well, you might notice that on a wet day, you drive a little differently than you do on a dry day. We've been talking about friction forces and how that changes with surface conditions. Well, in this case, I need enough friction between my tires and the road to allow me to make that circle. If the friction is not enough, or it gives way, then the car is going to continue on that tangential velocity. So if you're making a turn and the friction is not enough, there's not enough force pushing you in, then you're going to continue in a straight line. And so friction is one of our centripetal forces. Another force that could make things go in a circle is the force that might be on a string. Of course, we call that force tension. So here I have a cup of water and a rope, 4 ropes supporting my cup and a little plate. And it turns out that if I start to send this sideways, it wants to keep on going sideways. Well, that would be a bad idea for anybody that's sitting over there. They might get a second shower for the day. However, if I continue to pull in, then I can change the direction of this cup. And that can send the cup into a circle just by a tension force. We can also, of course, do that in a horizontal direction, which might make many of you duck. So tension is a force that can make something go in a circle, and friction is a force that can make something go in a circle. And of course, don't forget the big string that's tied to the moon that makes our moon go around the earth, you know, where every 28 days you gotta duck and not get hit by that string. Oh wait, that's not a string on the moon. That's a gravitational force that's making our moon go behave kind of in a circle. So our centripetal forces could be friction, or gravity, or tension. Let's take a look at a problem. Suppose that we have a rubber stopper connected to a string. And they tell us that the mass of this rubber stopper is about 13 grams. And the string is attached, or the rubber stopper is attached to a string that makes a radius of about 0.93 meters. This one's a little longer. And they swing the stopper in a horizontal circle where it makes one revolution every 1.18 seconds. And they want to know, what is the tension force exerted by the string on the stopper? So that feels like a long period of time, right, to twiddle this around. And if I do this as an example, and I allow this to create some tension and go in a circle, you'll notice that I have an angle between the shaft that I'm holding onto and the string. I can't make this travel in a perfectly horizontal circle because of course gravity is pulling on this. So this is definitely a physics land kind of type question. I mean, if I try to whip it out there, I could get that angle to be a little less obvious, but now you're trusting in my ability to tie a knot, so maybe we won't do that. But anyway, let's find the force that's acting on this that makes it go into a circle. So of course we want to label everything that we know about this situation. We know we have the mass is 13 grams, the radius is 0.93 meters, the period is 1.18 seconds, and we're looking for the centripetal force. So remember, our centripetal force F is m times AC, but they didn't give us the acceleration. Oh wait, well maybe I could use m times velocity squared divided by radius. Nope, they didn't give me the velocity either. What did they give me? They gave me the radius and the period. So this is where I can use the centripetal acceleration is 4 pi squared times the radius divided by the period squared. If I do that, and all of my units are correct, I end up with an acceleration of 26 meters per second. Then I multiply that by the mass. It's important to note that our mass was 13 grams, and I need my mass to be in kilograms in order to get a force in newtons. So I want to convert that to 0.013 kilograms. And if I multiply my mass times my acceleration, I get the tension force. So don't forget to convert. Make sure if you're given mass in grams, be sure to convert to kilograms. So we know that Newton's third law says that forces come in pairs. For every action, there's an equal and opposite reaction. And we talked about a force that's pulling something into the circle, into the circle, into the circle. And so we might wonder, well, if that's true, is there something that's throwing the object out away from the circle? And this kind of makes sense why we wonder about that, because how many of you guys do your own laundry? Hey, come on, that's not a difficult thing. You just throw those clothes in the washing machine, right? But after you've set the washing machine and gone away to go catch up on your favorite shows, and say you have a shirt in the washing machine, and you walked away, and when you come back, and you lift the lid, where are all those clothes? Well, the center of your washing machine tub has a little motor in here, and what it's going to do is, as the washing machine spins around and you look up and you're like, hey, all of my clothes are stuck to the outer edge of that tub. So we tend to think there must have been a force that threw them out away from the center. But here's what happened. When this first begins to spin and you have all of your socks and clothes and unmentionables inside the bin with the water, it's sent sideways. But what happens? It moves sideways and the can comes in and presses on the clothes, pushes it in toward the center. So then the clothes move in this direction and the can pushes it in. Then the clothes move in this direction and the can pushes it in. Just like the green blob or the car or the rubber stopper. There's a force that's pushing it in. And so when you lift the lid, you see that all the clothes have magically stuck to the edges of the can. But why does the can have holes in it? Well, when we go through the spin cycle, don't forget, we want to make sure that those clothes are spun dry as much as we can. We don't want to collect the water. So the water will actually leave along a tangential velocity just like this. It's important to note that the water doesn't go in a circle. The water is sent outward. So as the can spins and the water is not going to be allowed to press in, the water at this point is going to be moving in the same direction as the tangential velocity. So if we had water moving in this direction when it leaves the can, it's gonna leave at a tangential velocity, but it's moving here. Or if it's leaving the can from this direction, the water is gonna come out in a tangential velocity here. Or if it comes out over here, the water is gonna be thrown tangentially away from, not away from, why? Its object in motion stays in motion. The water was initially sent in that direction, so it wants to continue in that direction. It was coming off the top, that water would leave here like this. Object in motion stays in motion. This is just inertia. But to make things a little bit more confusing for us, some people have decided to give this, what seems like a center fleeing force, a name. And they call it centrifugal. The F in centrifugal might remind you as a fleeing force or away from the center. I need you to know that that F in centrifugal stands for fake or fictitious, because that is not a real force. This is just inertia that the water had. It's just gonna leave, it's gonna head in the direction that it continues to go. It is not a real force. But then of course we develop things that make it seem like it's a real force, like a centrifuge that will spin blood and sort out different parts of blood. And so it makes sense why we're a little confused about this, but a centrifugal force is not really a force, it's fictitious. The only true force involved here is the centripetal force toward the center. That's a real force. And we've seen that it can come from tension, or it can come from gravity or friction. And this is what makes roller coasters so much fun, because we like to make the loop instead of flying off in the direction that we were headed before. Okay, that's it.